So here we have an example of a capacity bound. You can show it per methods. So, oh, by the way, here we only have one channel N, right? We define the partial orders for two channels, but when you only have one channel, we mean like that the how the channel relates to its environment channel. So if for instance, if N is epsilon more capable than its conjugate channel, then we have these bounds here. Oh, by the way, Q and P here are always the quantum and private capacity. So for instance, if you have that N is epsilon regularized more capable, then you know that the private capacity is between the quantum capacity and the quantum capacity plus epsilon, for instance. So this is just one of the theorems in our paper related different partial orderings to capacities, just as an example of the sort of statement you can prove with these techniques. And as I mentioned before, I think that the really nice thing is that it gives you a very nice and simple way of for instance, obtaining capacity bounds from approximate gradability. Okay, now that we talked about our partial orders and capacities, let's talk a bit more about strong data processing inequalities. So these are related to the contraction coefficients we discussed before. And the discussion before really motivates us to find good ways of actually obtaining these contraction coefficients or understanding a bit more how these contraction coefficients behave. I mean, they also found many applications beyond just these less noisy ordering, so they are also interesting on their own. So, and many recent works have also worked on characterizing and computing strong data processing inequalities. So there's a lot of work, of course, on logarithmic supple inequalities, which can be seen as one way of obtaining strong data processing inequalities. Also in this conference, we'll have this talk on class-count-leap duality, also by Zuta et al., which is also a way of obtaining strong data processing inequalities. So these are just some works. There are many others now on strong data processing inequalities. And just a brief reminder, this is really when we have a strict data processing inequality, right? When we know that the say the relative entropy strictly contracts from between two channels. And here we'll show a bit more of the connections between hypercontractivity and strong data processing inequalities and the PETS recovery map. So let's gather some basic definitions. So first we'll define the PETS recovery map. So to define the PETS recovery map, we need two things, namely a channel and a state. And we'll define the PETS recovery map as this M hat over here. And this PETS recovery map is a quantum channel, which has the property, oh, and by the way, by star, I mean the channel in the Heisenberg picture. And the nice thing about the PETS recovery map is that if you apply it to the output of the channel, you'll see that it maps sigma to, the output of the channel to sigma. So in some sense, if you input sigma, let it go through the channel, and then apply the PETS recovery map, you recover sigma back. And Hayden et al. Showed that actually you have a strict data processing inequality if and only if the PETS recovery map does not only recover sigma perfectly, but some other state as well, some state rho. So if there's some other state rho, such that if you feed the output of M given that state to M hat, you'll recover that state as you recover rho as well. So we sort of see that the properties of the PETS recovery map should be related to strong data processing inequalities. And we'll work with the sigma weighted norms. So what are these norms? They are defined over here, and they are closely connected to sandwiched Rene divergences, which are defined over here. And there is a very nice paper by Reed and Müller-Hermes, where they show that the data processing inequality is actually equivalent to an inequality like this one. So if you look at the p-to-p norm of these weighted state norms, then this will contract if you apply the dual of the PET's recovery map. And the data processing inequality for the relative entropy is actually implied by having this inequality for a region around 1 for the value of P. And there's also some work by Simon Baigi, which uses similar techniques, and I think it precedes Müller-Hermes and Reeb to show such statements. And so what is more or less the intuition here? Well, you should think that these P norms, these weighted sigma, P sigma norms, they try to measure how peaked the state is weighted by the eigenvalues of sigma. So, you know, if you look at the L1 norm, this is usually the average over all space. So and the infinity norm is just the maximum. So of course the maximum is much more sensitive to peaks, localized peaks, than the average, right? And the P norms somehow interpolate between these two scenarios. And the P to P norm, being smaller or equal than 1 under this map, somehow tells you that a quantum channel will not make the peaks sharper, right? This is one way of understanding data processing, that somehow you will not be able to make the distribution more sharper and make the distribution sharper and more concentrated by applying a quantum channel. And now it's actually a fact that these norms are increasing in P. Okay, so this means that, for instance, if you have an inequality which tells you that the P to Q norm for some Q larger than P is smaller than 1, then it means that not only is the action of the quantum channel making you with smaller, this is having you smaller peaks, right? So go back to the intuition with the infinity norm again. If you have a function such that the average is equal to its maximum, right, then this function is constant. And so, for instance, if you think about the action of a channel, if you have that the 1 to infinity norm is smaller or equal than 1, for instance, then you would expect that the output of the channel is essentially constant. So you have, for instance, like a replacer channel. And these inequalities here, they interpolate these scenarios and these regimes. So if you have some P to Q norm, this is essentially telling you that how flat the outputs look under the lens of sigma. So, and this should be related to a strong data processing inequality, which tells us how indistinguishable or how flat the outputs of the channel become. And this is indeed the case. So we provide many tools how to work with inequalities like this one and get strong data processing inequalities. So in some cases, we even get equivalence in the sense that, like a strong data processing inequality is equivalent somehow to one of these hypercontractive inequalities. So just to showcase one thing we can prove is, for instance, assume that you have an inequality like this one. So you precompose the channel with the inverse of the PET's recovery map, and then the PET's recovery map, all in the Heisenberg picture, and you have that the P to Q norm is smaller than some constant C. And in addition, you have that the 1 to 1 norm is smaller or equal than 1. Then you can show that actually this inequality below here holds. And recall that this is exactly the sort of statement we were looking for in the less noisy ordering, right? By the contraction coefficient characterization, in the sense that, you know, if P is equal to Q, so this term over here is equal to 1, right? And if C is equal to 1 as well, you see that this term vanishes. So this just gives us relative entropy domination of one channel by the other. So this is just one example of how statements like this one relate to the less noisy ordering we were discussing before. And I should say that, you know, if you have some general channel here, then it might be also quite difficult to check this condition over here, or even, I mean, this condition is also pretty difficult to check. However, if you restrict to the case where n is the identity, so we are really interested in the contraction coefficient of n, no second channel involved, or as you were talking before, comparing to erasure channels, then we actually have that this inequality is for free, okay? And just, I mean, at least to me, it was not, when I started working on this, it was not immediately clear how this expression over here scales. So this inequality becomes stronger the closer P gets to 1 and the closer Q gets to infinity. So as I was saying before, this is this sort of average equals maximum intuition. In particular, if you have, as you can see, if we have like P going to 1, right, and Q going to infinity, this term over here will go to 0, which tells us that the intuition I was telling you before, that you essentially have a replacer channel, i.e. all the outputs are indistinguishable, indeed holds true. Okay, and I mentioned the Sandwich-Renyi divergences before briefly, and I must say that they work quite well in this whole business of proving data processing, strong data processing through hypercontractive inequalities. And in particular, a Renyi-2 version of this inequality I'm showing you here tensorizes, in the sense that if you can show it for one copy of the channel, you get it for arbitrarily many copies of the channel for free. Because this is not the case, at least we don't know to be the case for this relative entropy inequality, in the sense that, you know, if you have this inequality over here for one copy of the channel, it's not for free, that it holds for many. Okay, and that I already discussed. Okay, as I mentioned in the beginning, we also have some results regarding F divergences, which are one of the most general ways of defining functionals that satisfy a data processing inequality. There is not one way in the quantum way of doing this. So just do the standard and the maximum one, but we also discuss some other variations of how to define an F divergence in the paper. But yeah, essentially we start from some operator convex function f with the property that f of 1 is equals to 0. And then we also define the so-called modular operator for two states, which is just given like that. And then you can define the following quantity, which is usually called the standard F divergence between two quantum states. And you can also obtain the maximal F divergence by defining it this way. And this gives you a very large class of functionals that satisfy data processing. This class of functionals also includes the relative entropy, but much more. And you can also define the mutual information for this F divergence, I mean, for both the standard and the maximal one in this way. So you just take the relative entropy between AB and the marginals. Sorry, not relative entropy, the F divergence. And this leads to a natural notion of mutual information. And given this, you can then, of course, also define less noisy with respect to this F divergence over here. So every F divergence also induces an ordering of quantum channels by imposing the domination of the mutual information as we did before for the case of the relative entropy. And the interesting thing is that the connection between the mutual information characterization of the ordering, in the sense that, we say that one channel is less noisy than the other if we have this condition here with eta smaller or equal to 1 holding, is actually equivalent to a strong data processing inequality, or sorry, this sort of F divergence domination for the two channels. So this relation between less noisy and F divergence holds beyond the specific case of the relative entropy. And well, the proof idea is to essentially define a suitable families of states that you can input here and over here, and show that one reduces to the other in some right limits. Okay, and the other very nice thing is that, as we discussed before, if you have a contraction coefficient just for the channel, in the sense that we don't have two channels involved but only one, or another way of saying is that you take one of the channels to be the identity, then also in the case of the F divergences, you can interpret a contraction coefficient like that as just giving you a comparison with respect to an erasure channel with the erasure probability given by this said contraction coefficient. Now, the interesting thing is that classically, all orders coincide for all F divergences. So you don't really get anything new out of this, what I just discussed in the OK nice. You can construct these mutual informations, blah, blah, blah. But the orderings are all the same, because in principle, you can see that you can show that it all reduces to the ordering with respect to the chi-square divergence. Now I'll define it in the next slide, but it should be seen as like some sort of local approximation of an F divergence. But quantumly, we don't know that this is the case. So in principle, unlike the classical case, there could be many different orderings which are induced by many different F divergences, unlike the classical case. And we strongly suspect that this is the case because quantumly, it is known that the chi-square coefficients tensorize. So if you know what is the contraction coefficient of a channel with respect to one state, then you also know that the contraction coefficient with respect to many copies of the channel and the same product state. And of course, we don't have a proof of that, but we strongly suspect that this will no longer be the case quantumly. So in principle, it could be the case that we, instead of having just one ordering induced by F divergences, we actually have a whole zoo of them. And this also makes things a bit more complicated because the chi-square divergence is in some sense induced by a scalar product. So getting the ordering in the chi-square divergence is much simpler because you can actually work with some spectral properties of channels. Now, just what I just promised you, namely a definition of the chi-square divergences. So if you start with the set of functions such that minus k is operator monotone, and you have this weird relation but for the inverse, and the property that k of 1 is equal to 1, and you just define G to be the set of operator convex functions with the property that G of 1 equals 0, then in some sense, I mean, these guys over here give you F divergences, and the chi-square divergences are somehow local versions of the divergences over here. And to make this precise, you have this property over here, And also, just to give you a definition, this is how one actually defines the chi-square divergence, where this again is the modular operator and this is the right multiplication operator. So you can see it's really just like some sort of scalar product with the kernel given by the modular, and not exactly the modular operator, but this guy over here. Okay, and as I mentioned before, classically you have that if you have an ordering with respect to the chi-square divergence, then you also have a nomination for all other divergences. And this arises from a particular representation of the relative entropy or of any F divergence in terms of the chi-square divergence. So if you dominate it pointwise with the chi-square, you also dominate it everywhere, right? If you after you integrate. But this such integral representations for the relative entropy or more general F divergences in terms of this chi-square are not known to hold quantumly. However, we can still find a condition which imposes domination for all. So the mother of all dominations, similar to, in a sense, for instance, like degradability also gives you that, you know, the output of one channel always dominates the other. But we found this condition over here to imply that for all divergences, you have a domination. So if you, for a quantum channel n and some constant eta, you have pointwise these two inequalities, then you actually have that the output always, I mean, for any divergence with a function g, you have this property. And from this, you can actually go and show that, of course, you also have this property for the chi-square, because in some sense, they're just the local version of this. And as I mentioned before, the astonishing thing is that classically, you can actually go back and show the equivalence for each one. But unfortunately, in the quantum case, that's not clear or straightforward. But in any case, this condition seems to be the strongest one for two channels, because then you get this inequality for all possible pairs m and n. Okay, now I gave you many conditions. Let's also talk about some examples of channels. So one class of channels we discuss in more detail are the Weyl channels. So these are just so Weyl unitaries are just generalizations of Pauli matrices, and you should think really of random Pauli channels. So you, with some probability, you apply some Pauli matrix to your system. They have a very simple, so they have a very nice and simple mathematical structure. These Weyl channels. And for them, we are, for instance, able to find examples of channels that are less noisy, but not degradable. So for instance, showing that the less noisy ordering and the degradable order are actually not the same. That, you know, the requirement of one channel being less noisy is strictly weaker than it being degradable. And we also saw some other properties. We discussed these random Weyl channels in a bit more detail. And another class of channels which we discuss in a bit more detail are Gaussian channels. So for these, we show that assuming the constrained minimal output entropy conjecture for phase covariant quantum channels, so I would refer you to the works of Gua and De Palma, which proved these conjectures in some regimes of parameters like the one mode or entanglement breaking parameter range. And for those, under that conjecture, we can compute the contraction coefficients for attenuators, amplifiers, and additive noise channels and show that the contraction coefficients also tensorize. So also for this class of channels, we are able to provide some explicit values for the various contraction coefficients and obtain tensorization. So here are still some open questions. I mentioned a couple of them already, or actually all of them. So are, for instance, the completely less noisy ordering and the regularized less noisy orderings the same? Can we find examples of channels that are completely less noisy but not, sorry, that are regularized as noisy but not completely less noisy, for instance? And the same for the f-divergences. Can we actually prove that quantumly there are different orders induced by f-divergences, and how many are there? How many classes? So I think it would be nice to classify. I mean, first show that there are the different orders, and then try to classify them, of course. And another very important question is to study the tensorization of contraction coefficients in more detail. So this is, of course, a very hard question, but it would be very interesting to obtain more techniques to obtain at least also approximate tensorization for various contraction coefficients. And with that, I would like to thank you for your attention and refer to our paper, which is linked below for more details. You can also just Google me, Google my name, and you'll find my university email. I welcome all correspondence with questions or comments about our paper. And I guess you can also find my email at in the paper. And finally, if also during Beyond IID, if you have any questions just or comments or whatever, just drop me online on Slack, and I'll be happy to reply. Thanks a lot, and thanks again to my wonderful collaborators for making this possible. Thanks.